And today we'll be looking at equilibrium number 2, rotational equilibrium. And last day we brought in a new terminology, the word torque, and it's represented by the Greek symbol tau. So we can actually draw tau, something like that. And it is defined as the product of a force F and its lever arm D. The key thing to remember about this, though, is that the force and the distance must be perpendicular to each other. So you see that right here, torque is equal to force perpendicular multiplied by how far the force is being applied from some pivot point. So here's an example. If I drew some type of, maybe this is a seesaw, maybe it's something else, but if I call this the pivot, you see that this beam is going to pivot over this point right here. If I apply a force over here, the torque would be equal to the force multiplied by this distance, as long as this distance is perpendicular to the force. And torque is what causes rotation. So the easiest way to kind of think about this is think about what is something that, like, every single day you experience this, I guess, simple machine. We call it a door. If you picture a door like so, the door has some hinges on the side and the doorknob is over here. So the question is, why is that doorknob as far away as possible from the hinges? Hey, have you ever tried opening a door by pushing closer to the hinges before? If not, maybe just go up, stand up right now and see what happens. Is it easier to open the door if you push really close to the hinges or as you get further and further away? And hopefully you do notice that, yes, it is easier if it is further away. That's why we put the door handle as far away as possible. It maximizes the torque. So another way to think about it, if you want to cause something to rotate, you can either apply a large force close by, or you can apply a smaller force further away. You can also think about how a wrench works. So here's a wrench. So why is it easy to turn a nut in a bolt? So if you're just think of a single nut or bolt, like so, right here, if you try to turn this, you need to apply a large force around the nut, and that distance is very small. You notice how from the center of the nut or to the screw to the force is very small. So you need a very big force to apply. However, by using a wrench like this, what you're doing is you're maximizing that distance. You're increasing that D such that you can apply a smaller force in order to turn the bolt or nut or screw or whatever it is you are turning. We scroll down to here. So since only the component of the force perpendicular to the lever arm contributes to the arm's rotation, we label this component force perpendicular. So just to reaffirm what we just said about that whole perpendicular force, again, if I have some lever arm like so, and with some pivot, if I apply a force at some angle, we're actually losing some of that force just due to the fact that it is not perpendicular. So if I apply a force in this direction like so, the component of this force that's causing rotation is just going to be the Fy component. So this Fy will result in this rotation. So it brings in the trigonometry once again. Right, so in this case, torque for here would equal to the force. So force in this case is going to be sine theta times d. Okay, so force perpendicular times distance. Again, one final thing is, if you imagine that door, here's a door again with its hinges. If you ever just push along the edge of the door, it does not move. Right? Does not cause rotation. You have to push into the door handle or out of the door handle to cause that door to move.